Very pleasant morning to everybody. Today we'll be starting with a new chapter from the subject Advanced Soil Mechanics and Foundation Engineering, GATE examination and all the other examinations. This subject, this topic is very important. So today we'll be starting with stability of earth slopes. Okay friends, initially to begin with stability of earth slopes, we will discuss about stability number, and we'll also discuss about factor of safety, and with factor of safety there comes other definitions also. So we'll study about this. What is the stability number? Okay, so if this is the self weight, okay, self weight, this self weight causes instability and cohesion causes stability, and the maximum height of the slope, say for example this is the embankment and this is the slope formation, and the maximum height of the slope, that is HC, it is directly proportional to unit cohesion and it is inversely proportional to gamma, that is density of the soil. Okay, and HC is also related to phi. Phi is nothing but it is the angle made by the slope and also the angle of internal friction. This is what is the definition of a stability number. Okay, coming to the next definition, that is factor of safety. The factor of safety in a slope is the ratio of average shear strength, that is tau f, to the average shear stress. Okay, to the average shear stress, that is tau, developed by the point during the potential failure surface. Say for example, here there is a formation of slope and this is the potential failure surface through which the slope causes. At this particular point there is a development of potential failure, and the ratio of shear strength to the average shear stress is called as tau f by tau. Tau f by tau is nothing but it is a constant. Okay, and it also states that tau f is equal to constant into tau. That means tau f is directly proportional to tau. Okay friends, now let us study about some definitions related to factor of safety. So factor of safety with respect to average shearing resistance is nothing but tau f upon tau m. That means C plus sigma tan phi divided by Cm plus sigma dash tan phi m. Okay, next, factor of safety with respect to cohesion, that is C divided by Cm. C is the normal cohesion, m, that is Cm, is mobilizing cohesion. Next, factor of safety with respect to internal friction is equal to tan phi divided by tan phi m, where phi is the normal angle, phi m is the mobilized angle. Now let us discuss about the different assumptions of slope analysis. They say that stress is in the two-dimensional form. Okay, the second point says Coulomb's equation is applicable for C5 soils. Coulomb's application, we have already studied it in the stresses in soils. Just go back through it and you can understand. Seepage pressures are estimated from the seepage conditions in the water level. Say for example, this is the water level and there is a seepage force acting here. It is estimated along with the water table seepage forces, because seepage is caused because of the movement of water from the upper surface to the lower surface. With that the amount of soil is drained. That is why the seepage pressures occur. The conditions of plastic failures are estimated to be satisfied along the critical surface. Say for example, this is the ground level and this is the critical surface along which the crack is going to form, and there is a formation of slope, and the plastic failures are happening here, plastic failures. Okay, along with the critical surface only the plastic failures are going to be happening, and they are satisfied along the critical surface is what the last point says. Finite slopes and infinite slopes. So what is this finite slope? A slope is limited to the extent and bounded by the base and top surface. Base and top surface of the slope. Okay, the slope is limited to the extents of top and bottom. Okay, it is bounded, a slope of limited extent and bounded by the base and top surface. Base, top surface it is the extent of it, and it is bounded by it. Okay, it is the best example for the finite slope is embankments. Okay, this is the embankment. This is the best example. The soil strata is now homogeneous and they are parallel to the slope surface. Soil strata is parallel to the slope surface is what the third point says. Coming to the next slope, that is infinite slope. It is having a boundary surface of semi-infinite soil mass, and it is inclined to the horizontal. Okay, it is inclined to the horizontal. This particular slope is more inclined towards the horizontal, and they are semi-infinite. Okay, they are not completely infinite, it is semi-infinite, and the soil mass is inclined towards the horizontal, and they are having the constant soil properties for all the depths below the surface. Depths below the surface, it is constant properties of soil. The soil stratum is not homogeneous with the depth, but strata of different soils are parallel to the slope surface. Okay, this is the slope surface. Strata of different soils is parallel to the slope surface is what the last point says. Now let us discuss about the different types of failures. Okay, coming to the first type of failure, that is rotational failure. And the second one is slope failure. And in slope failure there are again two, that is toe failure and face failure. Okay, coming to the third type, that is base failure. Fourth one is translational failure. Fifth one is compound failure, and the last one is wedge failure. Okay friends, now let us discuss about the different types of failures. Okay, the first one is the rotational failure. What is this rotational failure? Okay, it occurs by the rotation along the slip surface by the downward and outward movement. Okay, this is downward movement and this is the outward movement. Along that there is a rotation taking place. Because of that, what happens? The rotational failure occurs. Okay, the movement of the soil mass and the slip surface is homogeneous. Okay, in case of homogeneous soil, there is a formation of circular slopes. Okay, when there is a formation of homogeneous, then there is a non-circular slope formation. So this is what is about a rotational failure. Coming to the slope failure, what is the slope failure? In this slope failure we have three types. One is toe failure, one is face failure, and one is base failure. Let us discuss about one by one. So in this picture you can see a toe failure. What is taking place? There is a failure along the surface that passes through the toe. Because of the surface which is passing to the toe, there is a formation of failure. Okay, this is called as toe failure. Coming to the face failure, what happens? The failure is along the surface that intersect the slope above the toe. Above the toe, what is taking place? It is called as face failure. Coming to the base failure, the failure surface passes below the toe. So it is the failure surface, it is passing below the toe. Okay, this is failure. Coming to the next part, that is the third one, that is translational failure. What is this translational failure? A constant slope of unlimited extent. Okay, it is the slope is unlimited and a lot of destruction is going to take place, and there is a steepening of the slope, and it has uniform soil properties. That means all the properties in it are almost of the same amount, and at the same depth there is going to be the excavation, and it is acting below the free surface. Say for example, this is the free surface, it is acting below the free surface, and when it is acting below the free surface, it is called as infinite slope. Okay, there are different slope for the layered materials. It is also having the layered materials. Say for example, it is having different layers, okay, before the formation of slope that is taking place below the surface. Coming to the next failure, that is compound failure. It is the combination of horizontal rotational slips and translational slips. Okay, there is both rotation taking place and also there is translation taking place. And you can see in this picture, it is curved at both the ends. Okay, in the left hand also it is curved, right hand also it is curved. It is okay. It occurs when there is hard stratum. When the strata below the surface is hard, that is there is a presence of rocks and boulders, that time there is a compound failure. Okay, it also occurs at the depth below the toe. Okay, below the toe only this failure is going to take place. Coming to the last part, that is wedge failure. In the wedge failure, what happens? The failure is along the inclined plane. So if this is the inclined plane, here there is a formation of failure. Okay, and here is a wedge and this is the plane of the inclination, and the blocks and wedges of soil mass are separated by the plane of interface. With this plane of interface, the blocks, boulders and different rock strata which is present below the soil surface, that is separated. So this is what is about a wedge failure. Hope you have understood the different types of failures. Okay friends, now let us discuss the different methods to improve the stability of slopes. The first point, flattening slope. Okay, say for example this is a slope, so there is a flattening slope over here. Okay, that what happens, due to which the tendency of soil mass to slide is reduced. So if there is a formation of the flattening surface, the tendency of the soil mass to come down because of the slope is reduced, and that causes the stability. And the second point says, say for example drainage is nothing but drainage of the different humus and all the important properties related to soil. So if it drains out, what happens? The stability will be reduced, and that reduction in the drainage, it helps the seepage forces. Seepage forces is nothing but, say for example this is the slope. Okay, because of the water, what happens? There is a seepage, that is flow of soil takes place, and hence it increases the stability. So if there is a more amount of soil mass is accumulated at the particular slope, that time what happens? There are chances that drainage will be reduced, and because of that, that will be increasing the stability. Densification by explosives, okay, bombarding. Okay, for example in a place where there is lot of soil mass, explosion, what happens? It creates the soil mass, and it makes the stability of the slope more easier and more efficient in order to perform. And vibroflotation, because of the certain vibration which is on surface, because of that it helps in the increase of the shear strength, that is tau, and also in cohesionless soil there is an increase in stability. That is what the third point. Coming to the fourth point, that is grouting. Grouting is installation of certain amount of big blocks inside the soil, and injection is also the same thing. Injecting the certain amount of important parameters inside the soil, and the camps in order to camps into the specific zones. Okay, say for example where there is the less stability, at that point there is grouting, and there is also injection of the certain amount of very hard particles in order to increase the stability. That is why the grouting is being done, okay, to make the land more stable and to make it more efficient in order to perform. Okay, for that the grouting and injection is very important. Coming to the last point, that is sheet piles and retaining walls are installed to provide the lateral support. Say for example this is the soil mass which is draining out. For that there is a presence of retaining wall which will provide the stability also for the ground surface, also for the movement of the surface bodies on the particular slope. So one of the very important method, that is friction circle method of stability of slopes. We have other methods also, we discuss one by one. So to begin with, this is the friction circle method. So here you can see this is the slip circle and this is the frictional circle, and the radius here is r, and this radius is itself also r. Because this is a circle, right? This is a slip circle, and with respect to this as center, this circle is drawn. So this is r, this is r. This is r sin phi m for the friction circle. Now coming to this circle, this is LC, this is theta by 2, this is radius, okay, and the elemental distance is called as delta L, and this is radius r. This is the weight of the wedge, and AB is the toe end, and this is the top end, and this is the imaginary circle, okay, with respect to which the circle and the downward surface is acting here. This is called as slip circle, and this is called as frictional circle. Now, what are the assumptions of this frictional circle method? The total stress analysis is for cohesive and frictional soil is the first point. In order to find out the factor of safety, the friction circle method is used. So there are three different forces acting on it. They are weight of the sliding wedge, cohesive force, reaction on slip circle, and the frictional resistance force is tangential to the frictional resistance is what the main point says. Coming to this diagram, so this diagram is schematically represented over here. So this is W, this is R, this is C. Now C is equal to Cm into L. C is nothing but cohesion, Cm is nothing but mobilized cohesion, and Lc is the length, this length, okay. A and B, whatever the imaginary point is connecting here, this is called as Lc. Tan phi m is equal to tan phi divided by factor of safety. Now what we have here, for the small elemental strip, Cm into delta L is the length, okay. For this particular strip, okay, delta L, for this particular area, what we have here is length is Cm into delta L is what we are seeing. And taking the moment along delta L, what happens? Cm into delta L into R, okay, R is nothing but the reaction over here, Cm into Lc into A. Now, delta L into R, Cm gets cancelled, delta L into R is equal to Lc into A, L into R is equal to Lc into A. This is summation of delta L, okay. Summation of delta L is L, and this is R, Lc into A. Now, A is equal to L divided by Lc into R. Now, this is what we have come to know. Here, Lc is less than L, A is greater than R, okay. This A is what greater than R, and Fc is equal to C by Cm. Here what has happened is, a factor of safety is equal to C by Cm is what we have considered here. So C becomes Cm into factor of safety. Here factor of safety is Lc, and Lc should be almost equal to factor of safety is what your last point says. It's about Swedish circle method, okay. For Swedish circle method, it is also called as slip circle method or Fellini's method in case of C5 soils. Okay, now let us study about this one by one. So here it is pure cohesive, that means phi is equal to 0, only C exists here. Here in cohesive friction soils, C and phi both exist. Okay, coming to the first one, that is purely cohesive soils. It has, okay, initially to begin with the Swedish circle method, the scientist has given certain assumptions for it. Let us learn the assumptions one by one. He says slipping circle is the arc of the circle. Slipping circle is nothing but the arc of the circle is what he says. Next, he also says that there exist two cases. One is for purely cohesive soils where only C exists and phi is equal to 0. Here for cohesive friction soils, C phi, that is C also has a certain value and phi also has a certain value. Now, for the first method, that is for slip circle method of purely cohesive soils, driving moment is nothing but W into x bar. So this distance is x bar, okay. It is moment W into x bar is what we have done here. Next, resisting stress tau f is equal to C plus tan phi, that is C plus tan phi is nothing but resisting stress, okay, for purely cohesive. Now, what happens? Resisting force is equal to tau f into A, that means C into L is what we have done here. Now, resisting moment is equal to C into L into R is the second equation. Now, considering the factor of safety as 2 by 1, that is 2 is what? Resisting moment and 1 is driving moment. Okay, resisting moment by driving moment gives you factor of safety, that is CLR divided by W into x bar. Coming to the next for C5 cohesion friction soils, it is also called as Fellinius method. Here you are considering the weight of the wedge, and N is the slip circle N, and T is what the tension acting here. So for this, the base of slice is a straight line. Base of slice is a straight line. Okay, that is what the first point says. So factor of safety is nothing but Mr by Md. Mr is nothing but the resisting moment. Md is nothing but the driving moment. Md is equal to T2 into R. So you can take any circle. Say for example, if we are taking for the second one, there is a triangle formation. Here this is T2 into R. So R as it is, you can write it here. Summation of T2 can be written as summation of T, which is equal to T. Now, what you have done here, Md is equal to R into summation of T, where T is the tension. Okay. Now, resisting moment is equal to tau F, that is C plus tan phi. We already know it. So F is equal to tau F into A, that is force is equal to whatever the resisting force we have here, Fr, or resisting moment also, what you can call it here, C plus sigma tan phi into A. So resisting C into sigma C plus sigma tan phi into A. Now resisting force F is equal to summation of C plus sigma tan phi into delta L into B. For unit base, what we have here, B is equal to 1. So this, if you internally multiply, it is C into sigma delta L plus sigma into delta L into tan phi. It happens to be resistance force is equal to CL plus sigma N tan phi into R. Coming to the resisting force, that is CL plus tan phi into delta N, tan phi into sigma N into R is what we got as resisting force. Say for example, this is the second equation. In order to calculate factor of safety, Fc is equal to 2 divided by 1. What is 2 here? Resisting force. What is 1 here? Mobilizing force. Okay, that is R into sigma T divided by CL plus tan phi sigma N into R. R gets cancelled over here. So factor of safety FOS or Fc is equal to sigma T upon CL plus tan phi into sigma N. So this is what we got. So hope you understood this Swedish circle or Fellinius or slip circle method for both purely cohesive and friction soils. To the last topic, that is Taylor stability number. So for this Taylor stability number, we have total cohesive force which resists the slipping of soil mass along the slip arc and at the critical equilibrium condition where slip arc is directly proportional to C, that is cohesion, and HC is nothing but the height of the slip circle. Now we have C into HC divided by FC into gamma into HC square is equal to HC and H here get HC and HC gets cancelled, only one HC is remaining. So C divided by FC into gamma into HC is what? Stability number. Stability number is nothing but, in order to stabilize the particular slope, we have a particular number at the critical equilibrium condition where cohesion and HC are directly proportional to the slip formation. Now factor of safety Fc is equal to CLR divided by Wx, that is weight of the sliding wedge, and x bar is the gravity, that is centroid. So L is directly proportional to Hc and x bar is directly proportional to Hc what we have. So W is equal to mg. So G is as it is, m is nothing but V into rho. So rho into G is nothing but sigma. V is as it is. So md is equal to W into x bar is equal to gamma into V into x bar is equal to gamma into H square. Now mr is equal to CLR. So Fc is equal to resisting moments divided by driving moment. So C into H divided by gamma into H square. So H and H get cancelled. C by gamma H is equal to factor of safety. Now Sn is equal to C divided by factor of safety into gamma into H. So this is the Taylor's stability numbers derivation.